Today, I am pleased to share with you our paper presented at CVPR 2024. In response to the remarkable capabilities demonstrated by large pre-trained models, the paradigm in computer vision and natural language processing has shifted from training task-specific models to fine-tuning a shared pre-trained model. The left figure illustrates the core idea of transfer learning, which leverages a model pre-trained on a large dataset as a starting point and customizes training models for each specific task. However, as the scale of the model increases, fine-tuning the entire model becomes increasingly challenging. This process not only consumes vast computational resources, but also potentially leads to overfitting and other issues. To address this dilemma, parameter-efficient fine-tuning techniques have emerged as a promising solution. The figure on the right illustrates three dominant PEFT schemes: adapter, VPT, and LoRa. Instead of updating the entire model during fine-tuning, these techniques focus on modifying a small subset of parameters or adding additional modules tailored to the specific task. This approach not only reduces computational costs, but also achieves competitive performance compared to complete fine-tuning. We analyzed current mainstream work and identified two major challenges with existing research. First, existing PEFT approaches lack a trade-off between preserving the capabilities of pre-trained models and effectively adapting them to downstream tasks. Second, there is a lack of a unified perspective for comprehensive understanding and evaluation of these approaches. In this work, we address these challenges by analyzing each pre-trained parameter matrix through the lens of singular value decomposition, breaking down the raw matrix into a series of terms. We revisit the working mechanism of the existing PEFT methods through the lens of SVD. Our goal is to establish a unified framework for understanding the delicate trade-off between preserving the generalization ability of pre-trained models and facilitating task-specific adaptation. As analyzed in the table, we believe that the adaptation-based approach disrupts the orthogonality of the original parameter matrix. Similarly, in prompt-based methods, the learnable tokens directly interact with the left singular vector in the equation. However, this direct interaction has the potential to excessively influence the tuning, deviating significantly from the pre-trained model. In contrast, we observe that the sole low-rank adaptation item of the LoRa method adapts weakly to each of the singular items when the dimensionality of the weight matrix is large. This slight perturbation may marginally change the weight spectrum and singular vectors, resulting in the representation capacity of the pre-trained model not being smoothly adapted to downstream tasks. To balance the trade-off between over-adaptation and under-adaptation in downstream tasks, we propose a simple yet effective method, namely, the RLRR strategy as shown in the figure. This strategy can be derived from the aforementioned unified framework. For any weight matrix in the MHA and FFN modules, we fine-tune the frozen pre-training parameter matrix using a residual structure. This involves combining the frozen matrix with a low-rank-based scaling and shifting operation. From the perspective of SVD, the scaling vectors and shifting vector can also be interpreted as adjustments to the rows and columns of the pre-training matrix. Similar to previous methods, our adjustments to the parameter matrices are linear operations. This allows us to seamlessly absorb the scaling and shifting operations into the original parameter matrices by reparameterizing as follows. RLRR achieves state-of-the-art performance on two benchmarks, VTAB 1K and FGVC. All methods leverage VTB/16 pre-trained on ImageNet 21K as the backbone. This underscores the superior design of RLRR, which uses the pre-trained parameter matrix as the foundation for the residual term, thus preventing the potential pitfalls of over-adaptation or under-adaptation in downstream tasks. To better understand the proposed method, we conducted ablation studies on RLRR. Results show that one-sided scaling tuning outperforms dual-sided tuning without the residual term, suggesting that excessive rescaling harms the generalizability of pre-trained models. However, with the residual term included, this trend reverses, highlighting the importance of the residual term. The figure shows that increasing the number of layers improves accuracy in all settings. The configuration with residual and rescaling applied to all modules performs best, so we adopt this design. We extended RLRR to CNNs by converting convolutional kernel parameters into a two-dimensional matrix, facilitating RLRR's application to CNNs. Experiments on SAFAR 100 demonstrate RLRR's portability to other models. Future work will explore its application in NLP. Thanks.